Okay. I'm going to talk about flexible linear degradation and survival models, or as you wish, failure time models. Joint work with Professor Rosângela Loschi and Marta Freitas. Well, first I'm going to talk about the degradation models. After that, I'm going to talk about the failure time survival models. Well, there are many situations where it's hard to observe failure. And in these situations, the estimates based on conventional failure time models, the estimates become very poor because you don't observe as much failures to let the model capture the failure time distribution. In order to solve this problem, there's been a lot of work trying to work with degradation path models, which intrinsically is to observe some characteristic linked to the failure itself, but not the failure. And you observe this degradation, this characteristic degradation long time, and try to extract the failure time distribution from this information. Okay. Here we have the practical situation that led our research through the years since I'm graduation and master in course and PhD. And we have this data set. We have car wagons. For each car wagon, we have 2 bogies. And for each bogie, we have 2 axes. For each axe, we have 2 wheels. For each wheel, we give some names. First, MA11, MN12, and the rest follows the same way. And for each position of wheels, we observe the degradation of the diameter of the wheels. We measure this degradation in 13 equally spaced times, and we have 14 wagons. Then we have for each position 14 wheels. So our sample for each position is 14. And we keep measuring this degradation. For example, we have this path here, and a failure happens when you cross a predetermined limit. As you can see, not all the wheels reaches this predetermined limit, which we call threshold, DF. And as I told before, when you don't observe failures, you can make our model use this information of degradation over time. An interesting thing is that the conventional models, they do not account for weird behaviors like skewness or atypical paths. Then what we are trying to do here is to consider in the model that the degradation rates can be atypical or skewed. So the general expression for the degradation models assumes that the jth degradation measurement for unit I is Yij. So I plays for the experimental unit, J plays for the times of measurements. The general model is like this. Beta I generally plays for the random effect. Gamma is the vector of fixed effects, and as I showed before in the model, in the paths of the degradation of train wheel data, we will neglect this gamma part of the model because all the wheels start with 0 degradation, so we won't have to estimate this gamma fixed effect. And we have an error term, usually is assumed IID, but there's a way to consider autocorrelation and things like that, because you can, if you are measuring the degradation in the same wheel, it's expected to have some kind of autocorrelation. But this model is simpler. We are just trying to introduce skewness in heavy tail. After that, we can think on considering models that are a bit more complicated. So a failure takes place when this degradation crosses the threshold df. And this is how we are going to extract the failure time distribution for the degradation of the wheels. Okay. So we consider linear degradation models, introduce skewness and have tail behavior. To achieve this, we will use 2 wide classes of distributions: scale mixture of skew normal and log scale mixture of skew normal. And this distribution will be set for the random effect that plays for the rate of degradation. So model 1, it has this structure. The degradation rate is 1 over beta. Why consider the degradation like this? It's because the other methods that were built for using Bayesian statistics, they needed this kind of relation, this form of the degradation rate. But it doesn't mean that you have to use this. For that method, you have to use this form. Otherwise, you won't get some closure over beta and time to failure, and it will not allow the method to be used. For our method, can be used even if you use 1 over beta or just beta in the model like this. So for beta, we consider these 2 families: scale mixture of skew normal. It has an age exponentiated to -1 there. That is the mixture variable. Style shade plays for the kind of mixture you want to input to the model. The form of the distribution is like this. It contains the skew normal used by Giuliani, Venturelli. And the other distribution we assume to beta I is log of scale mixture of skew normal. And it's just the log version of the scale mixture of skew normal. The advantage is the distribution to put mass of probability just over positive values of beta. If we choose the style shade measure degenerated in 1, we get the skew normal model. If we choose gamma ni over 2, ni over 2, we get the skew t model. If we choose h as a beta, ni 1, we get the skew slash distribution. So it's a very wide family. The log versions of the distributions are the same if we choose the same measure h for the log version of the SCM-SN distribution. Also, if we assume alpha, who plays for the skewness parameter, if we choose alpha to be 0, then we cover the non-skewed version of the distributions. So we assume that the measurements between and inside each path are independent, and we assume the errors are independent and identical distribution as a normal distribution with that sigma parameter, and the likelihood function will look like this: a product of normal distributions. If we assume the beta I as SMSN distribution, we can use a data augmentation scheme to ease up the construction of the algorithm. The calculus will get very easy. And besides that, we have this parameterization here that will ease up even more the algorithm. Victor Lachus likes to use this parameterization a lot. U1 and U0 are IID normal 0, 1. H is a random variable with that measure that we choose to mix the model. It has the parameter ni. Then if we write it conditionally, we have this hierarchical representation. And to complete the specification of the model, we assume that a priori the parameters are distributed following these distributions. GI, I forgot to change from Portuguese to English, is the inverted gamma distribution. If independently of the choice of the measure 8, which is very nice, the conditional distributions, most of them are in closed form. So the full conditional are in closed form. We can use Gibbs. For beta I, we don't have a closed form. But for the other parameters, we have a closed form. The only problem is when we choose the H measure, then we have to worry about what distribution we will fall. For each distribution, we will have changes in the full conditions of HI and Ni. If we choose the stylish H with mass at 1, we won't have problem because all the distributions, full conditions before, are already set, and we will use Gibbs, and for the beta I, we use the Metropolis or other sampling method. If we choose the measure 8 as a gamma distribution, nu over 2, ni over 2, we can set the prior for the parameter ni as proposed by Fonseca, 2008, and the posteriors get this form here. And the HI will have a complete full conditional closed, in a closed form. Well, after and before, because we have to extract the failure time distribution from this degradation model. To extract this failure time distribution, we want to make it for a future population. How do we do that? We calculate this probability, and this probability depends on the rate of degradation of the future object of the population. So to sample from this new object, the beta for this new object, we use a data augmentation scheme, and it can be approximated by counting the number of betas that we sample that are up to T over the F. So at last we have a sample of beta n plus 1, and we count the number of betas at time T that do not cross the T over the F. Well, after we've done this work, we noticed that it would be easy to consider similar models accounting for skewness and heavy tails for failure to to use it in conventional failure time models. So what happens when we think about failure time models is that recently there's been a lot of work and efforts to consider models, conventional failure time models that account for heavy tails, as in Barros and Cancho, and valejos in Skew, but none of them accounting for skewness. So the models we build here, they account for skewness and heavy tails. And it has, one of them contains the valejos in Skew model. She uses a shape mixture of Skew log normal. We'll make a log scale mixture of Skew normal distribution that contains a shape mixture of Skew normal distribution. So we introduced these models accounting for heavy tail and skewness behavior. We provide the full conditional that are very similar to the full conditionals of degradation models. We use an augmented data technique to deal with sensoring, to ease up the sampling algorithm, and to infer about survival function of future objects of the population. And we apply the developed model for the veterans' lung cancer data. So here we have to augment the data. So I'm going to present very fast. We have two models. One, the failure time is a scale mixture of Skew normal. The second one is a log scale mixture of Skew normal. We use the mixture representation I presented before, with that Li indicating accounting for sensoring or not. So, as I told before, the full conditionals are very similar. I'm not going to present here. The only significant difference is about that you have to sample from the censored times. And to sample the censored times is very easy. The full conditional is like this. A truncated normal on the censored times. For model 2, just replace Ti by log of Ti. So coming back to degradation path model, we've chosen the MA31 position of the train. And we set flat priors. We are going to work on how to extract information from the specialists to avoid use these flat priors, but for now we are using flat priors. And we will consider as well the Weibull distribution for the beta-i's. So inside the class, we consider the SM-SN class and log SM-SN class. We will consider the normal, log T, log T, Skew normal, log Skew normal, Skew T, log Skew T, and as the special cases, choosing the measure 8, and the Weibull distribution that is very used to model this type of degradation rate. We've noticed that for a future object of the population, the log Skew normal was the best to fit the data. That histogram, it's funny because we don't actually observe the failure times. There's a method to estimate the times of failure that is very poor, but it works very well to compare with the histogram of these pseudo failure times to the data. So as you can see, the curves that best fit the histogram are, I don't know if you can see there, but LSN model is one of the best. LST2, ST model is another one that's very close to the histogram of the data, the pseudo-failure times. We analyze as well the veterans lung cancer data. They have 137 patients, 6.6 censored times. The lifetime is measured in days. We consider the same flat pairs we use for degradation. Here are the Kaplan-Meier compared to survival function for each distribution we've adjusted to the data. The best ones were log skew normal, log skew T, and Weibull, but Weibull and log skew normal has some little bellies when we compare the Kaplan-Meier with the survival function. So we've chosen to consider the log skew T model as the one that best fits to the data. As future works, we introduced flexible models to accommodate skewness and have tail. It seems to be appropriate to analyze the two data sets. Future challenge, we want to provide a multivariate approach to jointly model the wheel's behavior, and we want to link linear predictors to parameters of the lifetime distributions to model the lifetimes in veterans data set, which was done by Barros, Valejos, and we expect these models will offer better estimates than the others. So, obrigado.
Any questions? No. Have you performed a simulation study or just on real data sets? Simulations or only real data?
Well, this is our calcanhar de Achilles. The sampling method we used is very, very slow. So simulation for now isn't possible. We are working to improve the sampling methods.
Okay, so let's thank Rivert again. Let's go to the poster session now.